Hello everybody and welcome to the first section on the computer vision course. In this section we'll learn the fundamentals on how to set up our environment for the course and learn a few basic things about images so that we can get ready to explore more advanced topics in the next few sections. Specifically we'll learn how to set up our environment. We'll be learning three different environment parameters that we have to set up, namely Python environment, the Jupyter Notebook, which is our favored IDE for doing development, and then OpenCV, which contains all the tools we need to deal with images and videos. We'll learn about image representations, how computers represent images, and how computers operate on images using OpenCV. As an example, we'll be using this image, which is widely known as Lena. This is a very popular image used in computer vision research. We'll see how these images are represented in color format, how they are represented in black and white or grayscale format, what's the difference in the internal representations of the computer between these formats, and also how does the computer actually store these images in different matrices and different arrays, and how we can use that knowledge to actually work with the images. We'll have a section on Introduction to OpenCV where we'll learn about how OpenCV does basic things like opening an image file, writing an image file, making a random image, understanding the properties of image, etc. And finally, we'll understand how we can work with camera. With Introduction to OpenCV, we would have learned how to work with files of images and generating images on our own. The last subsection in this section will look at how can we use our webcams to capture both images as well as videos and then save them to different files so that we can then use them for different purposes later. So this is going to be a very interesting section. I look forward to going through it with you. I'm hoping that you're as excited as I am, and let's go and get started. Thank you. The first things that we need to do before we start our projects and start learning about vision, images, and OpenCV is to set up our environment. We'll spend a few minutes just trying to understand how to set up the environment, what kind of software we need, and what kind of packages we need to install. So the first thing that we'll need is three different packages: Python interpreter, a Jupyter Notebook setup, and OpenCV. Python, many of you may already know, is the most widely used language for computer vision and AI. It's an interpreted language. That means every line is interpreted at a time. It's not a compiled language where you write the whole program and everything gets compiled and then executed. In this case, Python, every line is interpreted and executed before going to the next line. It's very widely used for computer vision and AI because it is very powerful to deal with a lot of data at one time, and it also is very easy to debug because of the fact that it's an interpreted language. We'll be using Python 3, which is the latest release of Python. I'll give you some pointers on where to install it from. The next package that we'll be using is Jupyter Notebook. Jupyter Notebook is an IDE or an environment that allows you to interact with Python. It's the cleanest way to execute, write code, and then annotate your work. You can write comments very nicely, then you can write code and then go through the different parts of the code one by one. It's very beautiful, it's very readable, and it's also cross-platform generalizable. So in case I write, for example, my code on Windows and somebody wants to take my Jupyter Notebook and execute it on, say, a Linux or a Mac platform, they should be able to do it without any problem. Jupyter also provides a HTML based interface, so you can actually open your browser and code in the browser, which is something that we'll be doing in this class as well. And last but not the least, we need OpenCV. OpenCV is a library. It's an open library, which means that the source code is available. It's a library for images and video analysis. So it's basically a big set of packages that's got a lot of functions in it that allows you to load images, work with images and videos, analyze them, do a lot of transformations to them, write them back to a file, etc. It makes your life really easy. If you understand the basics, then you can actually go and find the equivalent function for anything that you want to do with images and videos using OpenCV. Other needed packages we'll discuss as we go in this class. I think mainly we'll need some packages like Numpy for matrix and mathematics. And there'll be other packages as we go through the course that we'll need for different things. But we get started with these 3 packages and a package for OS support that I'll also mention as we go towards our programming lessons. So the first package that we need to install is Python, as I mentioned. And if you guys don't already have Python on your system, you can download it from this website, from python.org. I'm assuming that many of you or all of you already know how to install Python and have done some coding in Python already. If not, internet has a lot of resources to get started with Python. There's a lot of lectures, tutorials, etc. that you can go and learn from. The installation instructions are operating system dependent, and based on your own operating system, you can go to one of these links and basically go and install it on your operating system. Please make sure that you add the Python install to your operating system path. So there are different ways to update the path of your operating system based on which operating system you're using. This particular link here shows different ways to update your path. Path basically tells your operating system to look for the directories to look into when it's looking for Python. So when you are in any directory that you're doing your coding in and you say, I want to use Python, the operating system knows where to find it because you have updated the path. So if we can just take a quick look at these websites, the python.org is the first website that I mentioned. Here you can see that it has download section, and you can download the source code. You can download for Windows, Mac, and other platforms. So please choose the right package. Then you go there and you download the latest installation for that. And along with the installation or the download, you will also get instructions for how to install it. Also, more detailed instruction page, which you can also link from the previous page, is here, where we have instructions for each operating system. If you can look here in this table, they cover Windows, they cover Mac OS, they cover Linux as well through the source release. So you can actually download a tarball and then install it on Linux as well. And when you're done, you would like to check your installation. What you do is you open a command prompt in Windows or a terminal in Linux or Mac and just type Python. This should give you a prompt that basically is a Python prompt that also tells you the version that you have installed. If you get this, that means your Python installation has been successful. The next one is the Jupyter Notebook. There are 2 different instruction sets that I have put here. One is for Windows, another one is for Mac OS, and Mac OS should also work for Linux as well. Just going there, what you will see is in that website, you'll see how to install Jupyter Notebook on Windows. There are 2 different ways to do it. You could use Anaconda, which basically runs a remote server on your machine that allows you to do HTML based GUI for Jupyter Notebooks. Similarly, there's a pip-based install. You can choose any of the 2, and both of them are fairly straightforward. I personally use the pip, but it doesn't really matter. Similarly, for Mac OS, if you go to this website, you will find how to install Jupyter Notebook on Mac OS. Both of these do assume that you already have installed Python, so please make sure that you do Python installation first before you come to this particular window or this particular installation. And then again, like Python, make sure that your Jupyter Notebook is working. Again, you go to your command prompt and you type Jupyter Notebook as I'm showing here. And then it should basically open a server, and along with that, it should open up a web page, something like this, which shows a local host and a port number /tree. The port number is the same that it mentions in the command prompt when it's launching the Jupyter Notebook. And this is basically your Jupyter browser. And then within that, you can go to any directory and open the notebook, and we'll talk about that more when we start the coding. And finally, we'll install OpenCV. The instructions to install OpenCV are at this website, it should just be a 1-line install. If your Python is already installed properly, and pip is a package in Python, if they're already installed from the previous instructions, you should just be a single-line install for OpenCV, and you should have no problems. So if you look at this website again, going to the link, the first link there, it basically has all the instructions on installing, using it, and how to use it in your code also. And this is something we'll also use in our code. And finally, there's a function reference for OpenCV. You don't need it right now, just keep it with you. But if you see this particular page actually shows all kinds of different functions that OpenCV supports, GUI features, operations, image processing, feature detection. We'll be touching a lot of these subjects in the due course of this class. Keep this link with you because whenever you need a reference, you need to understand how a certain function works in OpenCV. You can come to this page and get that information. And finally, you need to test the install. If you already have Jupyter Notebook working, all you need to do is type import cv2 and execute this command. And if you don't get any errors, that basically means that your OpenCV installation is working fine. So since we just spoke about this, let me quickly show you how the install checks in my particular system. This is my command prompt. The first thing we'll check is Python. So all you need to do is type Python in the command and you get to this particular prompt for Python. So now I am in the Python environment. I could actually type a code like print maybe, say print hello and enter, and it prints hello. So basically my Python installation is fine. The version is 3.9.7. So we'll come out of this shell. Now let's see if our Jupyter Notebook is working. So as I mentioned, all you need to do is maybe first clear the screen and then we'll type Jupyter. Hopefully I'm getting the spelling right here, and notebook. And once you type this, what you see is that it will start launching this server and it automatically opens up this web page, which is a Jupyter Notebook. So in here I have a directory which I'm using for this class. So I'll just browse to that directory, and in that directory I will look at sources, and I have one Jupyter Notebook file. It saves the notebook file as IPYNB extension. So I'm just opening a blank file. In fact, I have been coding a little bit here. Let's just delete this all and show you if my OpenCV is working. So now I have an empty file, and all I need to check if my OpenCV is working is type import cv2. And then if I run this block in this or this cell in the Jupyter Notebook and I don't get any errors, it basically means that I'm good to go. My OpenCV is working. Obviously, my Jupyter Notebook is working, and Python used to interpret this line. So that means Python is linked in as well. So that's how you quickly test your install. And once you're ready, once you're done this installation process, we can then move on to the next section, which tells us about how to look at images, how images are represented, etc. Let's look at this grayscale or a black and white image of Lena. What a human eye sees in this image is a person, a background, some objects like the hat, etc. But that's not exactly what a computer sees or how a computer stores this image. The computer looks at a set of pixels or small dots in the image that have a value of color, intensity, etc. So in essence, this grayscale image is laid out as a matrix or a two-dimensional array of numbers. One way to think about this array is that we have an x-axis and we have a vertical or a y-axis and we have an origin 0, 0. Generally for images and in OpenCV, the 0, 0 or the origin point is going to be the top left corner of the image. So we start there and then we move in the x direction and we move down in the y direction. So any point in this image is actually an xy coordinate and a value. So we can say that, for example, 100 pixels. So we move 100 in x direction and we move 100 pixels in y direction. We come somewhere here. This is the location of x equal to 100 and y equal to 100. Now this location in this matrix here would have a value that would correspond to the color or the intensity of gray at that particular pixel. And when we combine all the pixels in the image, for example, if this were say a 400 by 400 pixel image, we would have 400 such entries, and the value at each entry would tell us what the color and the brightness of that particular pixel is. A way to represent that is just like a two-dimensional matrix. Here what we are seeing is that we have this matrix of numbers. We start at origin. I'm arbitrarily saying that the number is 33, so that basically means that the total darkness or the grayness of that particular pixel at that top left corner is represented by number 33. Similarly, the next pixel, the pixel after that, and we have this 400 by 400 as an example matrix that will have 16 and 40 times the number of pixels in the image. So that's a grayscale image, right? So we only need a gray intensity, color intensity number to represent this image. But what happens if we have a color image? Something like this, right? In this case, it's not enough to just say that one value will tell me what this pixel or any pixel looks like. Because for the gray and say between black and white, you have a linear scale. You can choose a number on that scale that will tell you how gray or dark your image is. But when you have a colored image, you can have almost infinite possibilities of combinations of different colors. So you can't just represent it with one number. So the way OpenCV represents color images is with a three-dimensional array. So we have our X and Y coordinates, but we also have another array, another coordinate, which is a Z or a Z coordinate, which basically tells us what is the contribution of each of the primary colors to this image. As an example, if we are talking about a BGR or a blue, green, and a red color system, in that case, there will be three different values on this z-axis or a z-axis. First one telling me how much of blue is there in that pixel, how much of green is there in that pixel, and then how much of red is in that pixel. So another way to look at it again is to see it as one matrix exactly like the one in the grayscale image that tells us about how much of blue is there at each pixel. So we have some number 33 again, and I'm just using a very arbitrary example. In fact, I'm using the same matrix for everything, but that's not true in real images. These values will differ based on the image and intensity. But we have a value for each pixel for the blue color. We have another matrix, which is the values for green for each of these pixels again. And then we have a third matrix, which has values for red for each of these pixels. So the ultimate color of each of these pixels is a combination of the value for blue, the value for green, and value for red. And as many of you may know, the three primary colors, blue, green, and red, can be combined in different proportions to give almost any color in the palette. So you can make any color out of these three based on how much of contribution is there from each color. So as we go in the course, we'll actually play with these colors. We'll try and understand what happens when one color is more and the other color is less, etc. But we have to keep this in the back of our mind that actually there is a three-dimensional array. Even though I have shown this as three different arrays, there's one array that's represented as a three-dimensional representation inside OpenCV that keeps the value of these three colors that are contributing to this image. Now, blue, green, and red is one way to represent it. There are different ways to represent colors in an image. We will stick with blue, green, and red for now, just because it's easy to understand and easy to work with images in this way. But as we go into the advanced lessons, we can actually look at other color schemes as well. Just one more look at how these actually are represented. So in each of the pixels now, I just talked about like a very simple example, but if you look at this Lena picture now, and if I divide it into different pixels, again, each of these squares is equivalent to a pixel, even though I think it's much, much bigger than a pixel. But let's assume that each of them is one pixel or one small area in the image that we are looking at. If you take that image, that area, and you balloon it up, now there are multiple pixels inside that small area, and you can see those small pixels now a little blurry, but each of them have their own color combinations. And if you can break those, each of them into a red component, a green component, a blue component, they'll be represented by these matrices. So the contribution of the first corner, if you look at the first corner pixel here, it has got 81 as the contribution from the red pixel, red color, 12 as the contribution from the green, and 75 as the contribution from the blue. So it is more red, a little blue, and very little green. So when you combine these three colors together, you get the color that's there at the top corner. Usually we represent each of these entries by 1 byte. So the values that can go are up to 255. So in this case, they are far, far less. So in fact, all three colors are not very high in terms of their contribution, but even within that, red is more than the others. In contrast to that, if you look at the last pixel at the corner here, we see that red is 217, green is 169, and blue is 156. So it's little more reddish than green and blue, which seem to be equal in their contributions, and hence a little brighter pixel at the bottom corner as compared to the one at the top corner. So hopefully you understand how the images are laid out. And now if we understand how these numbers look, we can now go inside and play with these numbers. And that's how we actually analyze, manipulate, and work with images. We're actually working with these matrices. And that's what we'll do in the next section with OpenCV. Since images are represented as arrays, one of the questions that one can ask is, should we be able to display any array as an image? So if I have any arbitrary matrix, that's a 2 by 2 matrix, or as an X component and a Y component, can I actually display it as an image? And conceptually, I should be able to do that. And OpenCV and Numpy allow us to do that. The steps to do that are as following. We will create any random byte array. Byte basically means that each element is one byte, and that's usually typically a value of one color of one pixel. And that's how we'll use. And then we'll convert that byte array to a Numpy array. The reason we need to convert it to a Numpy array is because Numpy is this Python package that's used for mathematics and heavy linear algebra-like functionalities. And OpenCV is highly integrated with Numpy, and it understands Numpy formats very well. So we'll convert this random byte array that we generate using operating system procedures into a Numpy array. And depending on what kind of image we want to generate, if we want to generate a color image, we will have 3 channels. That means 3 matrices, 2 by 2 matrices. Sorry, 3 two-dimensional matrices. And if we have a grayscale image that we want to generate, we just need 1 two-dimensional matrix. And then we will basically be able to output that array as an image. So we basically use an OpenCV function to give us an image out of that array. Once we have that, the grayscale image will look something like this. It's basically a bunch of random pixels, because each pixel value in that image is just a randomly generated byte. You may also recognize this as similar to the screen we get on our television sets if there is no signal sometimes. And that's mainly because that's also random pixels being generated. And in terms of color, it's very similar, except now we have some color values to these pixels, but they are still very random looking. Obviously, every time you run these programs, hopefully you will not get the same numbers or the same pixels, because we are randomly generating the numbers. But it's very hard to compare one image to another because they're all random. The one function that we should touch upon before we go to our Jupyter Notebook and try to do this exercise of generating random images is the image write function, because once we generate those matrices, we need to store the image somewhere, and OpenCV gives us this function called IMWrite that allows us to write an image to a file. The arguments that this function needs is the image file, which is basically the name of the file that we want to store our image in. This could be a path to a directory and a file name, and an extension. So for example, a JPEG or a PNG file. And then the image handle, which is basically refers to the matrix that we used to convert to an image before we saved it here. So with this, let's go and open our favorite editor, the Jupyter Notebook, and try and see if we can generate images from random numbers. Before anything, we need to import our favorite libraries. So we start with CV2. We will also need NumPy. And we will need OS. So OS is the OS operating system support library. This gives us access to system functions like random number generation, like displaying an image. And since these functions change between different operating systems, we need this library so that we can get specific functions to our operating system. If we run this particular cell and we don't get any errors, that means we are good to go. It has already imported what we need, and we can now add another cell. And this is the greatness about Jupyter Notebooks, that you can actually do one cell at a time, and you can even execute cells out of order if you want to. So now first thing we'll do is generate a random byte array. So let's call it random byte array. And we will use an OS function called OSRandom, but we'll first say that this is a byte array. and then we'll use the OS random or urandom function. Urandom is a uniform random function. Basically, it means that it generates random numbers using a uniform distribution. For those of you who have a background in probability theory would know what a uniform distribution is, but for now we don't need to understand that in depth. And we need to tell it how many random numbers we need. So in this case, let's say 120,000 random numbers. So we have an good enough picture to look at. So this should generate a random set of 120,000 bytes, because we're saying bytes, and put it in a flat one-dimensional array. Let's run this, no errors, so we can move on to the next step. Now we take this byte array, and as I mentioned, we'll have to convert it into a Numpy array. So a flat by flat, I mean this is still a one-dimensional array. We need a two-dimensional array at the end, but for now, let's call it the flat Numpy array. This is basically taking the Numpy function and calling the array function in there and using this random byte array that we just generated, random byte array. And now what this function should do is we'll take the random byte array and put it in the format of NumPy, which OpenCV understands. No errors again, so good to go. Now we have an array in NumPy, which is a single dimensional array. The next thing we'll do is take that single dimensional thing and convert it into a two-dimensional thing. So we have an x-axis and a y-axis value. So it kind of starts looking like an image. So to do that, what we use is a reshape function that NumPy gives us. Let's call this the gray image, because we'll start with the grayscale image. And we will use, we'll take the flat NumPy array and reshape it into a two-dimensional array. Since I have 120,000 values, random values here, we can divide it into, say, 300 on the x-axis and 400 on the y-axis. That should take care of 120,000 values. Yes. So let's run this. Looks like now we have a gray image, which is a two-dimensional matrix with these random values stored in x and y axes, exactly like the way we saw in the files when we were talking about how images are represented. So now the last thing we need to do is just save this gray image as an image. And here we will use the function that we talked about, which is the cv2.imageWrite. So this function allows me to save it. I'll need to give this file a name. So let's call it random gray image dot, it could be JPEG or PNG. Let's call it PNG. And I have to tell it which image to use. So the handle here is gray image. That's the one I want to store and save. Let's see if this gives any errors. Output is true. That means it should have created this file for me. And if I go to the directory where I have this code, since I have not given any path, it should basically be in the same directory as where this code is, which I'm keeping in this file called sources. And we see there is a random gray image here. And if we open it, it looks, a random 300 by 400 image, 300 pixels by 400 pixels image with random gray pixels in there. Exactly like what we thought it would be. So now if I had to just modify this program and say I actually want to print color images, and as you guys know, to do color images, let's say I want to do a color here. I go to this one and say BGR, basically blue, green, and red image. If I want to do that, I need to have 3 channels, not 2. So not 1, sorry. So I have to give one more argument which says I need 300 by 400 by 3. But the problem now is that if I do 300 by 400, that already takes my 120,000 bytes that I had. So I need to reduce somewhere so that I can actually use 3 of these arrays. One way to do it is just reduce this to 1. Since I have 300 already there, this 100 times 400 times 3 is still 120,000. So I have a smaller matrix, 100 by 400, but 3 of those. So giving me blue, green, and red colors. And now they can combine to give a color image. So I can take the same image. I take the BGR image here instead of gray. And let's say it random color image. Sorry for using COLOR. Some people use COLOUR. I'm just sticking with COLOR as color spelling for this course, but feel free to use what works for you. So we have changed these two, so we'll re-execute this particular line and we will re-execute this one again and go and check our folder to see if anything changed. Yes, we have a random color image now, and opening it gives us a color image, and as you guys can see, it's 1/3 the size of the gray image because we divided that into 3 different parts, and it has random color objects or pixels inside it now. So hopefully that gives you a view of how the images are represented and how you can actually use that representation to your advantage by generating random images at times. The next thing that we want to learn about, which is fundamental, is how to load images. So this was all about random images, looking at random pixels at random places in the matrix. But ultimately, we would like to work with real images. We would like to modify real images, understand real images. So to do that, we have to import the necessary packages first, and we've already done that. For example, the CV2, the OS, the Numpy, and then the function that we use to load an image is this function called IMRead. It's similar to IMWrite in the sense that IMWrite writes to a file. Here we give a file name to read, and then the flags tell it some additional instructions. We will use 3 different flags, -1, 0, and 1. One tells the image to be loaded as grayscale, another value tells it to be loaded as color, the third one tells it to be loaded as exactly how it is without changing any color values or anything like that. But if you go to the section that I showed you, the link I gave you about the help with OpenCV routines, you will see a lot more options for these flags that you can use to load the image. And finally, there's an image. You just basically load this image and you assign it to an image handle that you can then use in the rest of your code to manipulate this image or use it in any way you want to do that. And after you have loaded an image or you have created an image, in the last section, we actually saved the image to the file and then actually showed you the file there, the random image that we generated. But you can also just display the image right from within Python and OpenCV. You don't have to go to a directory. That won't save the image for you, but it will allow you to see how the image looks. So for example, while you are working on a program, you can keep looking at the image output, and when you are sure that everything is fine, then you can save it. So the function you use to do image saving is called, or image showing is called IMShow. Again, we need some title which goes at the top bar, and I'll show you an example of how the title looks. And then the image handle. So in this case, for example, the image handle from the previous file, we got this by reading an image. You could use the exact same image handle and it would display that image back on the screen. How does the title show? There is an example here. I'm trying to show the Lena picture, and at the top you can see it says my image title, and that's basically what you enter here in the IMShow that shows up at the top corner as well. We saw how we could use OpenCV to load an image and display it on the screen. Next, we'll go and see how we can actually do this in OpenCV and Python using our Jupyter Notebook. Jupyter Notebook, we start with imports already there, CV2, Numpy, and OS, something that we've already done in the previous subsection. We'll now add the command to load an image from file. Let's first see how an image looks as a matrix. So I'm not going to use a handle first. I'm just going to load an image. We'll use the cv2.imRead function. I have an image in my media folder called Lena s.jpg. I could have a PNG file and it could be loaded as well. It doesn't matter whether it's a JPEG or a PNG. -1 as an attribute for loading the color image. And if we execute this, we can see this array, basically the array that we talked about, right? How the images are basically multi-dimensional byte arrays. And that's what we see here. We don't see the whole information about the image, and with these dots basically mean that OpenCV is not able to display all the bytes because there are too many and they won't fit in the screen. And it also says at the end that the data type is uint8, which means it's a byte type, and each of these is represented as 1 byte. So each pixel has each color component being represented by 1 byte. So that also confirms how OpenCV sees images as arrays, multidimensional arrays. But we don't want to just display it, right? We want to use this image for different things in our programs later on. So we'll assign a handle to this image. Let's call it img. So now this image that has been read is now being referred by this handle img. So it doesn't display it anymore. It just stores the handle in the variable img. So now we have the image handle. Now we need to see how to display it. And to display it, if you remember, the command that we saw was the imshow command. So we will use cv2.imshow. We will need a title. Let's call it, let's say, my image title for now. So this should be the title that gets displayed at top. And then I need to tell it what image to use. And in this case, it will be the img image. That's the handle that we have just created. Now, if you guys remember, the problem with doing just this is that it will flash the image and it will quickly go off the screen. But we want it to be there for some time, so we will also use a wait key function from OpenCV. It's called wait, K is capital, and we'll say 0, which means wait indefinitely until a key is pressed. So the image will stay on the screen until I press any key. And once I press the key, I ask it to basically destroy all the windows that it has created. So it's a command for that is, or the function for that is destroy. I think A is capital, all windows. And it does not take any arguments. So let's run this. And hopefully we should have an image created and shown somewhere on the screen. So I think I had an older image. Let me just do this again because we are not able to see this, but here we go. If you have an older image open, you need to close that before a new image will get formed. So in this case, I did have an older image on the screen, but this is the image of Lena that we just loaded from the file and displayed it here. The other thing that I would like to show here is this flag that -1 basically means load a color image. But if I did a 0 as an attribute here, or the flag here, it would actually load a grayscale image. So now, the image is actually just grayscale pixels, not color pixels. So basically choosing that flag in your load image or IMRead will allow you to change what kind of image parameters you're loading. So we'll keep it at color for now for our next section. But if needed, we can also load a grayscale image or different combinations, which you can go to that website that I pointed to for OpenCV that has all the different options that one can use. Coming back to our discussion, one last thing that I want to touch in this subsection before we move on is how do we retrieve image parameters? So given an image like this one, it has different parameters. One could be just the shape of the image, right? How many X pixels does it have? How many Y pixels does it have? Which basically, what's the shape? How does the image look as a rectangle? The other parameter that it could have is size of the image, which basically means what is the total amount of pixels that this image has and how much space does it take and things like that, right? And the last one would be how much is each pixel being represented by? Is it a byte? Is it a 32-bit float? Or is it a 64-bit float? Is it a 32-bit data type? All that information is another parameter that each image will have. So OpenCV gives us functions or it gives us ways to get these parameters. The first one is called image shape. Image is the handle that we have already understood, and shape, by using the shape parameter, it tells you the X and Y coordinates of this image. The size tells you the total number of pixels in the image, which should ideally be the product of X and Y. And the last image D type tells you the data type, which is basically per pixel size of each image. How much is the size of each of these pixels? So let's see how one could use these to get these parameters for the image. So we've opened our Jupyter Notebook again. We will not recode the whole thing since we already have coded some of the information we need. So right after I load or I do an IMRead on this image, I'm going to just put a new cell in there that I will use to figure out these parameters that I was talking about. So the first one is, let's print so image is our handle img. Let's print the first one was shape, right? So this tells me the X and Y coordinates of the image. So just to be safe, I will read the image again and then print the shape of the image. So I see that it's 600 on the X-axis, was 600 on the y-axis, and there are 3 of these, so I know that it's a BGR or a 3 color as a color image. Now if I had this at 0 and I reload this image and I print the shape of this image, I only get 600 by 600. I don't get the 3. That's because the grayscale, as you guys know, is now just one 2-dimensional array. It does not need 3 colors. So that's the image shape. Let's now maybe add another cell and print the size. Image.size. So in this, it's a 360,000 pixels, which makes sense because if it's 600 on the x-axis and 600 on the y-axis, you multiply these two, you get 360,000 pixels total. Because this is a grayscale image. Remember, we haven't run this line yet, but let's run this line and actually load a color image. Now we know that this is a color image because it has 3 channels, and if I check the image size now, it's 3 times the grayscale image size, and that's why your color images take more space, because in this case a color image is 3 times the size of a grayscale image just because it has blue, green, and red matrices. And finally, let's check the total data type, or how is each of the pixels stored. So image.dtype, so uint8, that means each of the pixels is stored as 1 byte, which is true for a grayscale. For a color, each color pixel will be stored as 1 byte, so you would have 3 bytes for each of the pixels in your image. So hopefully that gives you a really good view of how images are stored and how OpenCV can be used to manipulate those images. In the next subsection, we'll talk about how to transform images and how to do some very interesting operations with images. First, we'll try and capture an image from the webcam. The function to do that is video capture. This is provided by OpenCV again. The format of this function is as shown here. We basically call the cv2.videoCapture with an argument. The argument is the camera ID. If you have multiple cameras on your machine, you can have multiple camera IDs. Generally, the only one camera if you have, it will be camera ID 0. And then there'll be 1, 2, depending on how many cameras you have. And there is really no easy way to find which camera is associated with which camera ID. What I suggest you do is you start with 0, capture a frame, look at that image, and that will tell you which camera is being used for camera ID 0, 1, 2, and so on. So you can then choose the right camera that you want to use. For example, in my case, I'm using one camera to deliver this lecture right now, so I cannot use that camera for the capture that I'm going to show you. So I'm using a different camera whose ID I have already found to be 2. The output from this function is a handle. In this case, we're calling it camera cap. This will basically refer to this camera device that we have opened for capturing in the rest of the code. After we have done this, we can then use this particular handle to get the frame from the camera. And the way to do that is to use the read function for this camera cap handle that we just created. And a read function will return one single frame, which basically is one image, and associate it with a return value, and then that return value can get assigned to this img or image handle. In fact, this function read returns 2 different values. One is a success or a failure that you can check to see whether your capture was successful or was not successful. And if successful, the image will be the handle to that image that got captured from the camera. Finally, once we have captured the image, we'll then release the camera device. Because if we don't do this, what happens is that Python still keeps the device open and you cannot use the camera for anything else because it's now associated and owned by Python. So you have to explicitly say that I'm releasing the camera so it can be used for other usage or even opened again by some other program for capturing video or images. And after that, it's like the previous steps that we have learned. We can then use this handle to display the image or save the image using imsave or imshow commands that we looked at previously in this section. With this, let's now go and open our Jupyter Notebook and try to see if we can capture an image from our webcam. So here we have our Jupyter Notebook. This notebook already has some code that we used in the previous subsections. Importantly, it has all the imports that we need for OpenCV, for Numpy, and for the operating system. It also has the code that I did not delete from the previous subsection on how to show an image. Since this code is pretty much the same, I didn't want to write it again and again, so I'm going to keep this cell. And between these two, I'm going to try and open my camera device and capture a frame from that. And if you remember, the first thing to do is create a handle. In this case, we are calling it camera cap, and this will be CV2, and video capture is the function that we call. And I will give it a device ID 2. As I mentioned previously, I already know that my device that I want to use, the webcam that I want to use on my laptop has been assigned an ID 2 by the operating system. Yours could be different, so you'll have to basically try from 0, 1, 2 and find out which device you want to use. So this particular function should now associate camera cap as a handle to this video capture device. If we run it, there's no error, so we can go ahead and add next line, which will actually allow us to then capture a frame from this device. So as I mentioned, we have two different arguments as a return value. One is a success or a failure. The another one is a handle to the image, and this is returned by a function called CV2. Sorry, I will use the camera cap handle, and I will read from this handle. And this should give me one frame associated to the image, and the return value should be either success or failure based on if the capture happened or not. So let's run this. We should ideally check for the return value to see whether it was a success or not. In this case, I'm just assuming that it's a success, but that's not what you should do in the code when you actually write it for a usage or an application. But since we're just showing how to capture images right now, I think this should work fine. So ideally, we should have an image that's been captured from this camera and stored in this image handle. And now let's try and see if we can display that image by running this cell. And you can see that my camera on the left side, which is on my laptop, has captured this picture of me when I ran this camera cap read. And it titles it as my image title, same as what I had asked the CV2 to title it as. Just to show you once more, I could look at this camera and do a camera capture again. Actually, I need to open the file again because right now the Python has not released the camera, so I do not need to open the file again. Actually, I can just capture another one and then try and display this. And you can see I'm looking at the camera in this case. Now, if I look at my camera right now, the light is still on, even though I'm not capturing any frames. That's because I have not released the camera yet. So what we'll do is right after the capture, we'll add the code to release the camera. And what we do is camera capture. This is the device we have used to capture the value. So camera cap dot release is our function that's going to release this camera for other usages. So that way, now that light should turn off as soon as I run this function, which exactly happened. I can't show you guys from here, but if you run it in your own environment, you should be able to see that the camera light goes off and now you cannot capture anymore. So if I want to capture again, I will have to start here, then run this again, and I can release the camera and then look at my image. And right now the camera has been released and my image is captured right here. So hopefully that gives you a good idea of how to use the camera device to capture images. Next, we will look at how to use the camera device to capture videos. Capturing videos from webcam is a little more complicated than capturing images, as we have seen before. In fact, to capture images, we need to know a few more things about our camera and the video that we want to capture. First thing is, what is the frames per second that the camera is giving us and the frames per second we need. By frames per second, what I mean is that if you look at a video, it's generally a collection of video frames coming fast at us. So it feels like there is motion in the stream, right? Ultimately, what we are seeing is just one image after another at a very high speed. And generally 30 frames per second is a really good assumption to start with because most of modern cameras will support 30 frames per second. But if you are, really want to sync your capture with the capturing speed of the camera, you should look at your camera documentation, or OpenCV provides some methods if you go to the manual to understand what frames per second your camera is supporting. The second thing we need to know is the camera resolution. How many X pixels and how many Y pixels can you get from the camera, so you can actually get the best image in the video quality from the camera. And here OpenCV can help. We can actually query the camera and it can tell us what's the best resolution to use. And then finally, because we're saving this as a video, we need to understand what codec we want to use. A codec is a way that video gets compressed so that it doesn't take a lot of space. If we had to save each frame by itself, it would take a lot of space, both for storage as well as streaming or transmitting it. So generally, MPEG-4 or MP4, AVI, these are all different codecs that you may have come across that compress the video into a smaller size, and we have to know what codec we want to use so that we can then save the video in a format that we can use it to play and transmit or transfer it to other computers later on. So how do you capture from your webcam? Some of the things are very similar to what we saw with images. We open a handle called camera cap, and this opens a video capture device or a webcam. I'm using the same ID as the last time, and there's no difference between capturing an image or capturing a video, because in the end you're capturing one frame multiple times to make a video. The second step involves finding out the frames per second that you want to take. So this basically tells the system or OpenCV how many times in every second do I need to take a snapshot so that I can then stitch it together to make a video. Again, I'm assuming 30 frames per second, and I think for most of the cameras this will just work. So we'll go with 30 for our example. And then comes the little more complicated part, which is what is my resolution? How many X pixels, how many Y side pixels do I need? Here we'll use an inbuilt function in OpenCV. Using the camera handle, we'll get a property called frame width that will give us the x-axis, the size of the x-axis, and the second parameter to the camera capture get will be the frame height, which will give us the y-axis of the resolution of y-axis. So size will end up to be a two value array. The first value is the x-axis size, the second value is the y-axis size. And then once we know our resolution, we know our frame rate, we will now open what's called a video writer handle. This will actually allow us to take these frames and write it using a codec into a video file. So we'll open a video writer in CV2, and this video writer will take two arguments. The first argument is my output file name. Why do I want to save the video? And the second argument is the encoding that I want to use. I'm using YUV. There are many other popular encodings. YUV is just like BGR, blue, green, red. YUV actually divides the channels in a different way. It uses luminance and contrast and things like that, but you don't have to worry about that today. Let's just say YUV is the format we use. We could have chosen something else based on what we want to do. You can take a look at the manual and choose a different encoding. And then finally, we capture from a video from our webcam. So the command to do that is exactly the same command we use to capture a single frame. We use camera cap.read, and it gives us two return values. One is a success or failure, whether the operation was a success or not, and then the handle to that frame. But one thing that you may observe now is this gives me only one frame. I need to get these frames multiple times and then pass them on to that video capture device that will then put them through the encodec and make a video out of it. So to do that, I will use the video writer. Remember, we opened the video writer in the previous slide to write a frame. So this video writer basically keeps collecting frames and then compressing them and writing them to this video file that I have already told the video writer to write it to. And finally, like the image case, once we are done, we will release the camera device from Python so that other users can use it and other applications can use it. But we have to make sure that before we release, unlike in the image case where we just needed one shot of the video, we actually need to make sure that we can get X number of frames depending on how long we want our video to be before we release this camera device. After releasing, the video should be saved on our disk, and we should be able to go to that folder and open that saved image or saved video and play it. Next, we'll open our Jupyter Notebook and try to see how to capture video from a file. So this is the Jupyter Notebook that we will use to capture video from a file. If you can see again, there is some pre-populated code in here. The first cell is our imports that I'm not touching. The last cell is showing an image. We'll not be using this cell because we are only capturing a video. The middle three cells are what I have kept there for some time because these are long statements of code and I did not want to just mess up spellings or any formatting. So I just basically kept these two statements here. These are the same what you saw in the PowerPoint files. So we could just use them, and for the sake of speeding this exercise, I just pre-populated these two cells. But let's go from beginning. We import what we need, CV2 Numpy operating system. And if you guys remember, the next thing is to open a video capture device. So we will say camera app. This is our video capture device handle is equal to cv2.video capture, and here we will give the device ID, which is 2 as I have determined earlier. So now this should open a camera capture device for us. Perfect. Next, we want to say what our frames per second will be, and we will assume it to be 30 frames per second like we mentioned in the lesson. And after that, the next thing we need to do is we need to figure out what's the size in X and Y direction of the resolution of each frame. Since I've already copied it here, I don't need a new cell. Basically, what I'm saying is that I will use OpenCV to get the camera properties for frame width, and I'll get the camera properties for frame height, and that I'll assign to size. In fact, what I can do is I can print this size here. Let's execute this command and then print the size to see what does the size look like. Let's run this. So 640 by 480 is the size of my camera image. So 640 pixels on the X direction and 480 pixels in the Y direction. We do not need this. It was just to see, debug what's the size. So we'll remove that print statement. Next thing we do is open the video writer, which allows us to write these frames that we will capture to a file. And as we mentioned, we use a CV2 video writer function. I am calling my file where I'm saving this, my output video.avi, and I'm using the YUV codec that we talked about in the files when we discussed how to capture videos. So this command, when I execute this, should open the video writer. It's giving me an error. It's saying it doesn't know what frames per second is. It's not defined. So maybe this one didn't get executed. Let's do the whole thing again. Start from here, camera capture, frames per second, size, and video writer now should be fine. So we have a video writer, we have a handle to write a file now. So next what we need to do is actually capture a frame. And if you guys remember, the function used to capture the frame, actually that's also already there. The return value and image are using a camera capture read function. Camera cap comes from the handle here, and I can get one frame out of this. So now I have one frame. I don't have a video. I have one frame, and that's assigned to this image function right here. So now I need to know how many frames I need to actually save. Suppose that I want a video for maybe 5 seconds, right? So 30 frames per second, 5 seconds is 5 times 30 frames per second. So that's the calculation I'm going to do, which would basically be, say, num frames, I will say remaining is equal to frames per second. Say 5 is the total number of time I need it for, 5 seconds, times frames per second. That tells me how many total frames in the 5 seconds. Minus 1 because I've already captured one frame in the command above. So I need to capture 5 times 30 minus 1 frames in the remaining part of this code. So since I'm going to be capturing these frames in a loop, I'll just make a while loop and capture them within that. So let's go to the while loop. So I'll say while, I already know that return value tells me whether there was success or not in capturing the frames. So while I have return value, which means while it's success, maybe we could just take this return value and rename it success so it makes more sense. So while success, so while I'm successful in grabbing a frame, and my number of frames remaining is greater than 0, I should be in a loop and I should try and keep capturing, right? And we already know how to capture. Before we capture though, I should write down this one frame that I already have captured to the file that I am saving for video. So remember, we opened this video writer as our handle, so I will use the video writer to write the frame, and the function to do that is write, and we can say image, which is the frame that we got here as the first frame of this video. Okay, so then next is we basically continue capturing. So all I'm going to do is copy and paste this statement to capture videos, frames rather, and read the next frame. And once that's done, I will decrease the number of frames that I need. Num frames remaining minus equal to 1. So num frames remaining is now reduced by 1, and this loop should basically run for 5 times 30 minus 1 times, as long as I'm getting success on reading this, and it should continue reading an image from the camera and writing it to that file using the video writer. And like the last time, let's not forget that we need to release the device once we are done. So in the end, we just basically say camera cap dot release. So this should release the device for us, and then other applications should be able to use this webcam. So let's go from beginning again, just to be sure that we are running all these and we have no errors. If there are, we need to fix them. And now we run this one and we release it. And I'm not running the show image because this code has nothing to do with an image. It has everything to do with the video. So now there should be a video saved in this file, my output_vid.avi. For that, I'll have to go and look at my directory, and basically look at the same directory where you are keeping your code. That's where it will save it, unless you tell it a different path in your video writer open. So you can see my output vid has opened here. And if I play this, you can see me talking from this camera angle, which is where I was capturing my device. And this is a 5-second video, about 4.5 seconds or so. So that shows us how we can use webcam to capture and store videos. And this also brings us to the end of this section. That brings us to the end of this first section. So as we complete our first section, just to summarize what we have learned in this section, we learned how to set up our environment for development, including Python, Jupyter Notebook, and OpenCV. We learned how images are represented, color images, grayscale images, and how OpenCV looks at images as matrices. These matrices are two-dimensional when it comes to grayscale images, and they could be multi-dimensional when it comes to color images. We specifically looked at the color scheme called BGR, or blue, green, and red, which is a 3-dimensional extension to the 2D array of grayscale image representations. We also then went and looked at an introduction to OpenCV. We learned how to create a new image using random bytes, how to save an image, how to load an image that's already in our files directory, how to display the image using OpenCV, and finally how to get parameters like size and shape and the data format of these images that OpenCV saves. And finally, we learned how we can work with our own cameras, our webcams, how we can open them, how we can release them, how we can capture images using the webcams and save those images, and finally how we can capture videos and save those videos. These fundamental lessons that we got in section 1 are going to be very useful as we go to section 2 and beyond, where we learn about more involved and advanced image transformations and look at how to understand what images have using algorithms, etc. I'm very glad that I was part of this journey with you for section 1. I hope that you enjoyed going through these sections. Please reach out in case you have any questions, and feel free to go back into the lessons if you want to look at something again or look at the code that's associated with these lectures. Thank you very much for joining me.